Okay, so in this video clip, we're going to estimate implied volatility for, in this instance, it's actually a call option. We're going to use a bisection function originally proposed by Fabrice Rouah, and it's the estimate is set up in C++ in this Google Colab. So basically, we write out the main CPP file, right? And in here, we have information relating to the Black-Scholes model. So to understand a little bit what's taking place here, we're setting up the Black-Scholes model, standard model, Black-Scholes 1973. And the put option has been inferred by using put call parity. Then we, if you like, the normal cumulative probability denoted by capital N here for the standard variate, which is D, right? It's it's been invoked by using Boole's rule here, right? And the advantage of using Boole's rule is that we get a higher level of accuracy for the normal cumulative probability estimates. And then the bisection function is basically, we have to do a low ball and a high ball guess. So we populate the value for just an A and a B. And we can see down here, there's a low ball initial guess and a high ball. So 7 denotes 700%, and A equal to 0.00 is just a minute amount, very close to 0, but cannot be 0 to initialize perhaps. So we go with this value here. And then the bisection function corrects. It runs through a series of loops until A and B converge here, and we've specified a tolerance level. The higher we make this, the longer the estimation takes. So if we run the estimate that we have here, now we know in advance that the implied volatility, the volatility here consistent with the market value of, now we have here 757, which in fact is, okay, we probably need to change that to, let's change the dividend to 0 for a moment and change this value here. We can use it later on. So I'll just park it down below and do this, but it's 1045 for Black-Scholes, 1045.506. If we use the Black-Scholes model and inputted S equal to 100, K, which is the exercise 100, risk-free rate 5%, maturity of the option 1 year, no dividend, then the value of the option would be 1045. With implied volatility, we take the market value of the option and we would try to infer what the volatility is. Now, from experience, we know with these parameters, with this combination of parameters, that the volatility of 20% would produce a value, a model value of 1045.06. We're going the opposite direction here. We're saying in the market, the option, which is a call, is being reported as 1045, and we want to back out the value of volatility consistent with this market value and the other parameter values. So when we run this estimate, we should get 1045, right? Now, what happens? We write the main file. It gets set up here in the content folder. You can see that. And then we estimate, we come down and we estimate out the value of the option, and we're getting 20 cent, all right, but it seems to be an issue around a character before, so perhaps it's, yeah, it's probably this what's causing. So I'll just cut that out. Cut. Okay, I'll just delete. I'll copy first, and then I'll delete. Run it again. execute. So out, put, still getting 20%, which is correct. But there is a small conflict here on put call. Let's see. Put call was not declared in the scope. Okay, we put call and put call. C. Let me see. It's looking. We do have C here in inverted commas. That's fine. Put call, and we declare put call before. Let's go up. Yes, we have put call here. Did I say double? I said character. Okay, that would be fine. Put call equal to C. It is a character, because it's denoting, it's a symbol for the call value of the option. Okay, so perhaps the issue at stake here is we're missing a semicolon. Let's try that. Run, and then run again. Okay, and we get an exact result. Okay, so it's working fine. Any issues that arise are purely my own malfeasance, if you like, and we can put in the value we had here before also, and I think it's going to run fine. So that's fine. And I'll stop the video here.